The history of geotechnical engineering, and more particularly the history of soil mechanics, is very rich. So today we're going to review briefly what were the main developments before the 20th century, throughout the 20th century, and what we think that is coming up. Here we go. Look at some of these names, like Archimedes, Coulomb, Laplace, Terzaghi, Taylor. Do you recognize them all? I'm sure there are many others that you will know, and I will invite you at the end to make a list of them and to explore their lives and contributions. But let's see how we can put all these names together, building the foundations for our field. If we look at mechanics, we have to start by the origin of effective stress. Everything in granular media is controlled by effective stress. And all this begins really with Archimedes. Remember, he was taking a bath and he realized that there was a buoyant force that was lifting him up, and that was equal to the weight of the displaced volume of water. Fillinger in the 1913 published a very important paper that made him famous, but also put him in contrast with, apparently, with what Terzaghi would later promote, the concept of effective stress. And so at some point there was an open discussion between them, a forum, and things didn't work out very well, apparently, for Fillinger. And the story, it didn't end up well for him and his wife. So you may want to read about him. And later on, Maurice Biot really went beyond to recognize that also not only the skeletal stiffness, but also the mineral compressibility and the water compressibility, they were all interacting. And that led to the concept of poroelasticity, which typically we do not mention much when we talk about near-surface soil and geotechnical studies, but they are critically important as we go deeper into the subsurface, for example, in the area of petroleum engineering and CO2 geological storage, etc. The whole strength of soils is of frictional nature, and friction was an important topic even 5 centuries ago. Leonardo, you saw the sketch in the front, the beginning of this presentation. Leonardo understood the importance of friction, and he got it almost right. And the whole idea that the heavier the weight, the heavier had to be the mass to slide it in shear. But it was really Amundsen who understood the concept very well. And today we know his criteria as Amundsen's laws. The paper by Coulomb, 1776, was one of his many contributions, and it was really the concept that is still being used and drives our field whenever we talk about shear strength. His concern at that time was how to get sheep out of the shipyard. A major contribution to the understanding of friction really comes in the 1950s by Bowden and Tabor. But let's remember once again that the behavior of soils is all related to the granular nature, and that deformations tend to be all localized at contacts, whether they're under normal load or shear load. And all that begins from understanding the wheel. The essence of the wheel is that the normal force goes through the center to the reaction point where it receives an equal and opposite reaction. And therefore, we don't need much of a force to move it because there is no couple that needs to be overcome, contrary to the fact that instead of having a circular wheel, we have a square wheel. Hertz, the same Hertz who proved the existence of electromagnetic waves, recognized the importance of contacts in the deformation of two spheres in contact. And in the 1950s, Mindlin and co-workers were looking at the contact between two spheres under shear. While these studies were for spherical bodies, Greenwood explore the implications of surface roughness when two contacts come into play. And then there were two theories to also involve the adhesion forces, which are not very important for silts and sands, but will become increasingly more important for clay-sized grains. And those two theories follow the names of their lead authors, JKR and DMT. These are contacts and particles in contacts, and when we put them all together, we have the emergence of the macro-scale properties of soils. The first ones to explore this were actually to look into the phase transition between gases and liquids, and they simulated that with spherical particles. That was Alder and Wainwright in the 1957. Almost 2 decades later, Kundal developed the discrete element methods based on a similar concept, and the field of molecular dynamics, which really starts in the 1950s as well, it begins to take off with the power of computers, and both discrete element methods for granular materials and molecular dynamics to study materials at the atomistic and molecular scale took off in the 1970s. Now, another important characteristic of granular materials is the tendency for them to contract or to dilate upon shear. The first one to recognize was Reynolds in 1885. And you may recognize the Reynolds name because that is the one that was the same fellow that was studying fluid flow and the transition from linear to nonlinear flow regimes. And Reynolds number is the same Reynolds. These concepts really get beautifully captured for the context of soils in Taylor's book in 1948, where he understood that it wasn't just about packing density, but also about the extent of confinement. The higher the confinement, the lower the tendency to dilate. Rowe made a theory out of it, and all these developments get caught into the concept of critical state soil mechanics and the seminal book by Schofield and Roth. The field of mechanics has also had an important implications, and Rankin was really writing a book on applied mechanics, but he already introduced the theories to understand the concept of earth pressure. But really, the one who brings all these pieces of information together into the geotechnical field is Terzaghi in his fundamental book, the book that really takes off our field, and is the Erdbaumechanik book. Please find a PDF of this book and use translation tools. Look at the table of contents. It's humbling. Mechanics also help us understand another very important process, that the formations are very rarely homogeneous. That comes from the theoretical point of view in the work by Hill in the 1962, Rudnicki and Rice in 1975 put it together with the geotechnical, geomaterial constitutive model, and then beautiful experimental and theoretical work follow, including by Verdulakis and co-workers. Now, we not only should look at the granular skeleton, we should also look at what is happening in the pores. That means transport, whether it is advective or diffusive. On the advective end, the story begins with Bernoulli, who recognized the importance of the total energy. In other words, the elevation, the pressure, the kinetic energy on fluid flow. Laplace gave us the differential equation to tell us how that total energy is varying in a space, in a steady state seepage. And Darcy recognized the relationship between the flow velocity and the gradient of the total energy. The understanding of the meaning of the concept of permeability really comes from Hagen and Poiseuille, who were looking at fluid flow in tubes, in cylindrical tubes, to highlight the importance of drag along the walls. In other words, drag along the mineral walls that confine the fluid flow in soils. And Koseni and Karman bring it, the theoretical developments to the context of porous media. For diffusive transport of chemical species, the story begins with Fick's, and you may remember the first and second law. The one who understood the meaning of the diffusion coefficient was Einstein, and he related it to the thermal vibration and random walk. Smoluchowski and Knudsen gave additional contributions. Knudsen is an interesting one. It applies particularly for the case of gas flow in narrow pores, for example, shale gas, or any gas diffusing between clay particles, for example, because the mean free path before a collision between gas molecules may be actually longer than the distance between particles. And now diffusion is controlled not by molecular to molecular collision, but by molecular gas molecule to mineral wall collision and adsorption effects. Now, in the same pore space, we may have immiscible fluids, water and air, or oil and gas and water. The fundamental conception comes from Laplace. He understood these capillary interfaces. Young recognized that the interfacial tensions between the three different phases that were involved defined the contact angle. And then there is a beautiful story about that involves Anne Pockels and Lord Rayleigh. And Pockels was self-educated, and basically with kitchen utensils, he developed measuring technologies and understanding of interfacial tension that were revolutionary. Years later, other researchers actually got Nobel Prizes with the techniques that she developed. But Lord Rayleigh recognized the importance of her contributions and helped her get published in some of the leading journals of the time. In our field, beautiful work on unsaturated soil behavior was already taking place in Australia in the 1950s, and Bishop is the one who tries to put together the effect of suction in water with the concept of effective stress from Terzaghi in this mixed blend of concepts that we call Bishop effective stress. However, Fredland and Morgenstern recognized that these were acting at different scales and at different boundaries, and so it was better to separate them into distinct axes. The concepts were brought all together between the capillary suction and the critical state soil mechanics by the Barcelona school in the late 1980s. Now, if we look closer into how water and minerals interact, and we go almost to recognize the molecular scale, we realize that in those closest, let's say, 10 nanometers, things are unique. We don't pay attention to 10 nanometers when you have silts and sands because the grains are so large and even the scale of roughness is much greater than this layer. But that layer becomes very important in the behavior of clays, as you have seen in other parts of this series of seminars. The developments in this adsorbed layer start with Helmholtz in the context of electrodes. Wade and Chapman developed the theory, Stern corrected it for adsorption effects, complexes, and the fact that there are also not point charges, but they have their own scale, the atomic scale. For practical applications, Atterberg developed what we now know the Atterberg limits to be able to classify sediments for agricultural purposes. That is later embraced by Casagrande in a 1932 paper. In the meantime, Goldschmidt did a beautiful test. He mixed clays with water and he mixed clays with carbon tetrachloride. Remember, water is a dipole, while carbon tetrachloride is a perfectly symmetric nonpolar molecule. In one case, he observed that the clay had plasticity when mixed with water. However, when mixed with a nonpolar molecule, it was totally feeling like a sandy material, totally non-plastic. Therefore, this clearly highlights the importance of the water molecule polarity in double layer phenomena. All these concepts keep building up to understand the implications of different fluids in soils, in particular the role of contaminants. And Jim Mitchell's book in 1976 creates the foundation for this fundamental knowledge for the field of geoenvironmental engineering for the 1980s and the 1990s. Finally, as you see, we have taken a look at the physics and the mechanics and the fluids, and there was one science that was missing, and that was the biology, which really emerges when Van Leeuwenhoek developed the microscope, which in itself is amazing because the lens was known for 200, 300 years by then, and Galileo has used the lens to look at large bodies far away, the telescope. Well, Leeuwenhoek actually used the lens to look at the small things nearby developing the microscope. And he realized that water was much alive because it was full of microorganisms. And that is the beginning of the biological sciences, and for us, bioengineering. The field of biomediated, bio-inspired processes in geotechnical engineering is really a development of the last 20, 25 years. I'm going to pause here for a second to go back to look at an amazing time in the history of an individual with tremendous impact in our history, and that is Terzaghi's time in Istanbul. He arrived in 1916. He left 9 years later in 1925. In the meantime, he developed pretty much the whole concepts of earth pressure, effective stress, seepage and piping, friction, clays and consolidation. To understand soils, he had to confine them and create chambers and test cells. So he developed the odometer, the permeameter, the shear box, and he recognized the potential of using scale models. And he also wrote the book Erdbaumechanik, where he brings all these concepts of mechanics already developed for the last 150 years into the field of geotechnical engineering, creating the theoretical foundations for our field to emerge. So when we look back at the last 100 years and in the 20th century, we see that there were different drivers: the infrastructure, the wars, the airfields, dams and tunnels, the two earthquakes, the Niigata and the Alaska earthquakes that really shook the field, and the whole area subdiscipline of earthquake engineering and soil dynamics emerged. And then the environmental field, when we realized by the 80s that we have caused a significant environmental damage with the amazing growth, urban and infrastructure growth of the 20th century. So what will drive the 21st century? In the meantime, the 20th century also saw beautiful developments, most elegant laboratory and field characterization tools. Geophysical methods were amazing. We wouldn't have oil and gas today without those geophysical developments. In fact, supercomputers were developed for the geophysical field, not for medicine or biology or games or military purposes. It was developed for geophysical applications. And numerical simulations really has revolutionized our field, from finite elements to the discrete elements and molecular dynamic methods that we were talking before. There has also been an amazing revolution in sensors and the amount of data that is now available. And I'll come back to that in a second. But before I leave this slide, let's recognize that these developments have gradually brought together the earth sciences and the mechanics and the physics and the chemistry, and more recently, the biology to our field. So what about the IT revolution? is made possible by one amazing development, the same way that the lens allowed for the telescope and recognizing that we were not the center of the universe, and the microscope and recognizing that there was life at the micron scale. This is the other revolution of the last century, which is the amount of transistors that could be put in a chip. It has doubled every 24 months, which means more than 50 million times since we walked on the moon 55 years ago in 1969. This is amazing. And of course, when there is such a technological revolution, it has to affect all aspects of our field and all aspects of our lives, as we know very well. So if we stop one more time and think, what have been the important questions in our field? And we can use Google Ngrams to search for these words. So soil mechanics was really big and important and driving in the 50s and the 60s and diminishing in the 70s, and while foundation engineering was still advancing, and then the earthquakes brought us the concerns for sand liquefaction, and the 80s, the geoenvironmental field. And what is coming up now? Because all these other ones seem to be diminishing as we have already solved most of the challenging problems. Well, if you look at words like sustainability, climate change, coastal resiliency, carbon storage, energy storage, these are the new drivers for the geosciences, geoengineering, and our field. So to look back into the history of our field, I strongly encourage you to look at these 3 articles from the 1985 International Conference in San Francisco. They're just beautiful. To understand more the father of our field, Carl Terzaghi, take a look at Goodman's book. You will see not only his amazing mind and energy and drive and inspiration to the community, you will also recognize the individual in his full characteristics and flaws as well. It is a wonderful field. You will also remember many other names that I didn't cover. Make a list, explore their lives and their contributions.